Good morning. My name is Andros Jojo, and today I will be presenting an overview of quantum computing, a revolutionary field that is changing how we approach computational challenges. So I will be helping you to explore more about this quantum computing matters and how it differs from the classical computing. So as a real world applications and challenges we must address for its advancement. So let's get into the slides. So here are our contents. So uh, we'll be going to each slides one by one. So quantum computing overview. So, quantum computing is a new computing model based on the principles of quantum mechanics, so which represents a paradigm shift from classical computing. So, in classical computing process, informations are used using bits, which can only be 0 or 1. But in quantum computers, we are using qubits, which can be 0, 1, or both at the same time due to superposition. So this unique property enables the quantum computers to solve certain complex problems much faster than the classical computers. So quantum computing is not meant to replace the classical computing, but to complement it, helping in areas where the classical computer struggles, such as optimizations, drug discovery, and cryptography, things like that. So why does quantum computing matters? Uh, so now let's explore why the quantum computing is important and the industries it impacts. First thing is solving complex problems. So enables breakthrough in medicine, material science, and AI by solving the complex problems. Classical computers which cannot handle it efficiently. And second thing is boosting artificial intelligence. It enhances machine learning models by improving the pattern recognition and data analysis. Third one is enhancing cybersecurity. So it introduces quantum cryptography, protecting sensitive data against evolving cyber threats. Next is advancing healthcare. It revolutionized the drug discovery through molecular stimulations, leading to faster and more precise treatments. Transforming material science helps in designing novel materials with optimized properties, reducing waste and improving the industrial efficiency. So, evolution of quantum theory in computing. So, to understand the quantum computing, we first need to explore the evolution of quantum mechanics and how it changed computing. So, the first is classical versus quantum physics. So, the classical physics follows the determining rules where the results are predictable. Quantum physics introduce probability, uncertainty, and entanglement, which enables the quantum system to behave unpredictably. And the key discoveries that shape this quantum computing is Planck's quantum theory, Einstein's photon concept, Bohr atomic model, Schrodinger's wave equation, Hinsberg's uncertainty principle, things like that. And in 1981, Feynman's vision, besides Richard Feynman, he proposed that the quantum computers could efficiently stimulate the natural quantum systems, paving the way for quantum algorithm research. So that's one important turning point for the whole quantum algorithm research. And after that, there are early theoretical contribution made by David Dodge in 1985. He proposed the universal quantum computer model. After that, Charles Bennett, he explored reversible computation and quantum teleportation. Peter Shor and Low Grover developed quantum algorithm for factoring and research, things like that. So, what's a major difference versus quantum versus the classical architecture? So, now let's compare the classical and quantum computing models. So you know that classical bit it only have zeros and one, but in case of quantum qubits can exist zero, one, or both. Because they can deal the superposition. In classical bit it deterministic, but in quantum qubit it's probabilistic. In classical bits it's non-entanglement. Quantum qubits it's about entangled state. So this quantum computers work differently. So classical circuits use AND or and NOT gates for the logical operations. The quantum circuits use Hadamard, C0, and phase gates, leveraging the superposition and entanglement for the parallel processing. So quantum systems solve complex tasks exponentially faster than the classical computers, but faces a scalability and error correction challenges. So how quantum computing works? We need to unlock the power of quantum mechanics. So quantum computers leverages the qubits and quantum mechanics to process data differently from classical computers. The first one is qubit and superposition. So qubits can exist in multiple states simultaneously, allowing the parallel computation. Second is parallel processing. The quantum computers evaluate multiple possibilities simultaneously, enhancing the computational efficiency. And third one is a quantum entanglement. So entangled qubits remains correlated even when separated by large distances, enabling secure data transmission. So quantum algorithms exploit these properties to achieve breakthrough in optimization, cryptography, and AI-driven applications. So uh, the other quantum thing, quantum computing and how it's work like we deal with the qubits and superposition, parallel processing, quantum entanglement. The next fourth one is quantum algorithm. So quantum algorithm, which means it leverages the superposition and entanglement to solve the complex problem faster than the classical algorithm. So Shor's algorithm is one of the example for that. And its key application is another point. So applications including drug discoveries, material science, financial modeling, cryptography, addressing challenges intractable for the classical computers. So it's how the quantum computing works. So now moving to next slide, here we are dealing with the types of qubits and its implementation. So this is one of the most important part we need to know about the quantum computing. So this leading physical realization of qubits. So first thing is superconducting qubits. So as you can see, it's fast but sensitive to noise. Second thing is trapped ion qubits, which is highly stable but slower. Um, so you can see that these um, are things, these are two important points. So the superconducting qubits, it's used by IBM and Google, and trapped ion qubits, it's IonQ and Honeywell. and in topological qubits. So it's a error resistant based on Majora Fermons, so by Microsoft. And fourth one is photonic qubits, operates at room temperature, suited for communications. So Zenandu, quantum like that. So each qubit type has a trade-offs impacting scalability and reliability of quantum computing system. So different quantum hardware architectures enables practical quantum computing. So that's all about the types of qubits and its implementation. So now let's move on to next slide. It's quantum programming language and its tools. So programming quantum computers require some kind of specialized tools and framework. So these are the three major things implemented by the three major MNCs, one from IBM, one from Google, another from Microsoft. So Scikit, it's by IBM. So it's a Python-based framework for quantum programming and simulation. That's one is Silk by Google. So it optimizes for near-term quantum devices, enabling efficient quantum circuit execution. Uh, Another thing is by Microsoft, which focus on fault-tolerant quantum computing, which offers a robust integration with classical systems. So it's all about the quantum programming languages and tools. There are still many more developed by different MNCs, but as of now, these are the three important or most common programming languages and tools we are using. So let's take quantum error correction and fault tolerance. Well, I think we have mentioned it earlier also. So the quantum computers faces error due to decoherence. So error correction method helps to mitigate this problem. So there are basically four major types of errors. One is a quantum error type, another one is surface and a stabilizer code. Third one is a logical and physical qubits. And fourth one is a threshold theorem and its model. So this quantum error type, which means it's bit flip, phase flip, and decoherence. So the surface codes have 2D grid structure for error detection, and there's logical and physical qubits. Uh, Encodes data redundantly across multiple physical qubits. So it uses error correction to mitigate noise and enable practical, scalable quantum computation. The last one is a threshold theorem and model. So uh, there, if an error stays below 1%, scalable quantum computing becomes feasible. So fault tolerance is a key for practicing quantum application. So that error correction helps to mitigate all those problems. So making quantum computing more reliable. So next thing is quantum machine learning. So machine learning benefits from the quantum computing's computational advantages. So you can see quantum enhanced feature space, variational quantum classifications, and hybrid quantum classical neural networks. So let's get into each topic. So this quantum enhanced feature space means uh, it expands the classical data mapping using quantum kernels. The variational quantum classifiers, what it's doing is it's a hybrid quantum classical models, refine the prediction to iterative optimization, and the last one, the hybrid quantum classical neural network. It combines quantum circuits with classical AI to improve machine learning capabilities. So the quantum computing enables new AI techniques that classical system cannot efficiently execute. So these are the few examples for that. So quantum machine learning, QML, that's a revolutionary AI with quantum advantages. The next one is quantum annealing and D-wave system. Oh, what do you mean by quantum annealing and D-wave system? So quantum annealing focus on optimization problems, like quantum tunneling and its applications and things like that. So quantum tunneling, it escapes local minima efficiently. So specialized optimization evolves system towards low energy solution using quantum tunneling. So next one is D-wave architecture. So the D-wave machines using the supercomputing qubits enables high connectivity and large-scale optimization with some practical use cases. But there are some limitations and its applications are quantum annealing focus on optimization, unlike gate-based universal quantum computers. Its major application includes logistics, ML feature selection, and financial portfolio management. And real-world pilots include the industrial pilots in traffic flow, supply chain, financial demonstration, quantum annealing potential were classical heuristic fault. So traffic optimization, the portfolio management, and ML feature selection. Those are the important applications that we are using quantum annealing and D-wave thing. After that, we are moving into our next line, which deals with the ethical and legal and societal challenges that so there are some risk and responsibility in this quantum progress. So So we need to go much more deeper. So quantum computing raises significant ethical concerns. So quantum advancements raise the ethical consideration that must be addressed like a data privacy risk. So quantum decryption threatens existing encryption models. Quantum armories means governments investing in quantum research for cybersecurity and intelligence applications. So there are few ethical and legal and societal challenges that we will face, or if we need to tackle all those things. So we have deal with all these things, and what's a future roadmap? So, and I ask you to fault tolerance. So, quantum computing will evolve in phase. So, this NISQ era means they have said that it's from 2025 from present to 2023. So, it's a noisy hybrid quantum system dominated near term development, and the quantum tolerant the fault tolerant computing. That's something after 2030 plus. So there it will happen the logical qubit and error corrections, unlocking the practical quantum applications, things like that will be happening after that. So this is as of now the roadmap they have done. So as of now, we are standing in an ISQ era. So we can see there is some timeline and industry forecasts. So firms like IBM, Google, Microsoft, everyone are forecasting practical quantum advantages within the next decade. So with fully fault tolerant quantum computers likely by 2030s or later. So its benchmark and metrics, quantum volume, circuit depth, coherence time, and error rates are emerging standards for measuring the quantum hardware progress and guiding industry development. So, what's a real world quantum use cases? As we have mentioned it in drug discovery and molecular modeling, and in finance risk analysis are some very beneficial because the normal machines are not able to do it. So in drug discovery, quantum stimulation accelerate pharmaceutical research. So in financial risk analysis, companies like JP Morgan, Goldman Sachs, etc. They are using quantum algorithms to improve the portfolio optimization and trading efficiency. So these are the real world quantum use cases. So industries are pilots driving quantum innovations. So these are the online references that I have taken in place. So if you want to know more about what's quantum computing, things like that, you can just go to these links. So let me conclude it. Quantum computing is a rapid advancing revolution industry and computing paradigm. While technical challenges remains breakthrough in quantum hardware, error correction, algorithm development will shape the future of computation. So I would like to thank you all for your time, and I would be happy to answer any questions you have. Thank you.